Let's review how we rationalize Bernoulli's principle using the conservation of energy method. We have here a pipe that has a variable cross-section, and we mentioned that whenever the cross-sectional area is large, the speed of the fluid must be low, and wherever the cross-sectional area is small, the speed must be high. And that's due to the continuity equation, which I've shown right there. Then, for each section of the pipe, there are three aspects of energy that we have to deal with: a kinetic energy portion, a potential energy due to gravity portion, and a potential energy due to fluid pressure portion. And the sum of these three must be the same for this left section of the pipe as for the right section of the pipe. And in the previous lesson, we decided that since this left side has a slow-moving fluid, that the kinetic energy portion of the energy is going to be less. And on the right, since the fluid is moving faster, the kinetic energy portion will be larger. Since the centers of mass of the left side and the right side are at the same elevation, the potential energy due to gravity components, in this case, happen to be the same. And in order that these three things add up to be the same as these three things, it necessarily follows that this pressure has to be larger than this one on the right. So, the conservation of energy idea brings us nicely to the Bernoulli equation, which is the conservation of energy, but with units of pascals instead of joules, which is what we've always used for conservation of energy. So it's essentially conservation of energy, but we use the unit of pascals instead of joules. And here we have it. The pressure plus rho GH plus 1/2 rho V squared for one portion of the pipe must equal that sum for a second portion of the pipe. And here you can see that, unlike in my example on the previous slide, the center of mass of this portion of the pipe is at a different elevation than the center of mass of this portion of the pipe. You can see on the left, H1 is less than H2. So if this were our pipe, in the yellow equation up here, this quantity on the left would be different than this quantity on the right. If the pipe is level and the centers of mass of the water, let's say if it's water, are the same height above some reference line, then those two would cancel each other out, and hopefully we'll get a chance to investigate that further. So here's our problem. A level pipe carries water under pressure. At one point, the water's speed is 0.48 meters per second, and its pressure is 24,500 pascals. In an adjacent section, the pipe is constricted. The water's speed increases to 3.27 meters per second. Find the pressure in the adjacent section. So, we're going to use Bernoulli's equation, and let's predict. We're asked to find the pressure. Let's predict if the pressure in the adjacent section is going to be higher or if it's going to be lower. Well, let's see. The speed increases. Here it's going more slowly. In the adjacent section it's going more quickly. And according to Bernoulli, fast-moving fluids exert lower pressure. So we're going to guess that our answer should be less than 24,500 pascals. The rho GH term is going to cancel on each side of the equation because this is a level pipe. The two sections, the centers of mass of the two sections are at the same elevation. So those two quantities disappear from the equation, which leaves us with the left side. There's our pressure, 24,500, and here's our kinetic energy term, 1/2. There's the density of water, and there's the speed squared. On the right side, we don't know what the pressure is. The speed has increased to 3.27 meters per second. we still have the same density of water, and there's our kinetic energy quantity on the right. If we show some work as to what the numbers come out to be, we see that the pressure is less, just as we predicted. We predicted that we'd have a lower pressure than 24,500, and it's 19,300.